Okay, so I'm going to apologize in advance for the low budget recording here, the low budget video. I am doing this pretty late at night. And since I'm not going to be in class, I wanted to just make sure you had a couple of examples to go by. Today, you're going to be looking at sum and difference formulas, and it's an extension of trig identities. The sum and difference formulas don't appear all that often in trig identities, but they are useful for kind of simplifying expressions that we might not otherwise be able to do if we don't have a calculator. So you should have a yellow sheet in front of you that says Notes, Sum and Difference Formulas, with the sum and difference formulas at the top of it. Those same sum and difference formulas are on the not so fundamental side of the identities sheet that I gave you the other day as well. So I'm just going to take you through a couple of examples and do my best to explain in my absence today. All right, so example A says find the exact value of cosine of 15 degrees. So sum and difference formula are actually more useful for examples like this as opposed to the trig identities. You will see them a little bit in the identities. We'll do an example of that as well. But it's actually more useful for something like this. So like back in the day when we didn't really have calculators, or good calculators, we would need a way to calculate the cosine of 15 degrees. Okay, so now something you should notice is the cosine of 15 degrees, this can be written as 45 minus 30. Okay, and why did I pick 45 minus 30? Well, 45 and 30 are things that we can easily find the cosine or sine of. Right? So that's the idea of these sum and difference formulas, is can we rewrite expressions in terms of angles that we know the sines and cosines of. So those would be your special angles, right? Your 30, 45, 60, 90, 0, 180, things like that. Okay? So I can rewrite the cosine of 15 as the cosine of 45 minus 30. All right, and we have a formula. If we look at our sum and difference formulas, this is the cosine of a difference. So that formula on our sheet says cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. Okay, so if we call, I'm going to use the same colors here. So if we call 45 alpha and 30 beta, we can go back and substitute into this portion of the expression here. So we can write this as, we can write cosine of 45 minus 30 as the cosine of 45 times the cosine of 30 plus the sine of 45 times the sine of 30. And now you have to remember your special angles, your unit circle, your special triangles, whatever, however you like to remember them. Unit circle is best at this point because we're going to be using that a little bit later as well. A 45-degree angle is here, right? And we should know by now that the cosine of a 45-degree angle is radical 2 over 2. It's the same as pi over 4, right? We've been using a lot of radians, but we're going back to degrees a little bit here. So the cosine of 45 degrees is radical 2 over 2. Okay. The cosine of 30, that's the short triangle here. The cosine of 30 is radical 3 over 2. Sine of 45 is also radical 2 over 2. And the sine of 30 is 1/2. And now I could simplify this expression. Radical 2 times radical 3 is radical 6 over 4 plus radical 2 over 4. So the best I could do here is just write it as one fraction like that. All right, so again, just to review, we started out with the problem, the cosine of 15. So these sum and difference formulas allow us to write some angles in terms of angles that we can easily find the cosine of or the sine of right? Really, you're thinking about sine or cosine or some trig function of, right? And you're going to want to do the best you can to write these angles in terms of 30s, 45s, 60s, any combination of that. If it was in radians, you'd be looking for pi over 3s, pi over 4s, pi over 6s, etc. And so once we've rewritten cosine of 15 as cosine of 45 minus 30, we can apply the cosine of a difference formula that we have on our identity sheet that says the cosine of alpha minus beta is equal to this big long expression. Right? We could substitute, right, for alpha and beta, substitute 45 and 30, and then you go ahead and evaluate. So the cosine of 45 is right here, cosine of 30 is right here, etc. You evaluate, you add the fractions, and you're done. Next example, example B, says find the exact value of sine of 7 pi over 12. Okay, so this is essentially the same type of problem. We're in radians now. So we need to figure out some way to write 7 pi over 12 in terms of radians we know, keeping in mind that our special angles in radians are the pi over 3, pi over 6, and pi over 4. So you need to figure out, well, how can I write 7 pi over 12, or essentially 7/12 in terms of these, right? And so it's, it takes a little bit of getting used to, but hopefully you recognize, or with a little bit of trial and error, you can recognize that 7/12 or 7 pi over 12 is the sum of pi over 3 plus pi over 4, right? And if you don't believe me, we can go over here. Pi over 3 plus pi over 4. If I have common denominators, that means I get 4 pi over 12 plus 3 pi over 12, and there's my 7 pi over 12. Okay, so at this point, I have the sine of pi over 3 plus this plus pi over 4, right? So I've just rewritten 7 pi over 12 as pi over 3 plus pi over 4, and I can apply the sine of a sum formula. Look at my sheet. That tells me that the sine of alpha plus beta is equal to sine of alpha cosine beta plus cosine of alpha sine of beta. And I can now go ahead and substitute, right? So I've got sine of pi over 3 plus pi over 4. Okay, incidentally, order doesn't matter because we'll be taking the sine and the cosine of both, so it doesn't make a difference which order I do it in. But the sine of pi over 3 times cosine of pi over 4 plus cosine of pi over 3 sine of pi over 4. All right, so remembering pi over 3 is that 60-degree angle there. So that's our tall triangle. Sine of pi over 3 is radical 3 over 2. The cosine of pi over 4, that's our 45-degree angle, our isosceles triangle, that's our radical 2 over 2. Cosine of pi over 3, same triangle over here, but the x-coordinate is 1/2. And the sine of pi over 4 is radical 2 over 2. And we simplify as we did before. And coincidentally, it's the exact same answer we got before when we did the cosine of 15 degrees. So that was just a coincidence with the numbers. The way the numbers worked out, it's not always going to work out that way. But the idea is the same whether you're doing a cosine of a difference or a sine of a sum. We're really just applying the formulas here. All right, the third example has us finding the exact value of an expression that's already been expanded. Right, so we have to figure out which sum and difference formula has been applied and work backwards. So we've got sine 80 cosine 20 minus cosine 80 sine 20. And if we look at our sheet, right, this looks like the sine of a difference formula, right? So if we look at the sine of a difference formula, we see sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. So it looks like the sine of a difference. So we can rewrite this as the sine of 80 minus 20. right? These two expressions are equivalent, right? So this is the same as this. Well, 80 minus 20 we know is 60, right? So we're really just finding, this entire expression is really just finding the sine of 60 degrees. Okay, and again, that 60-degree angle is our tall triangle. The sine is the y coordinate, so this is radical 3 over 2. Okay, so working backwards is actually, in a sense, a little bit easier. You have a little less math to do, right? And you're trying to kind of whittle it down to a nice simple angle that you know how to find the trig ratio of. All right, this next example is my favorite kind of example. You guys might not like it, but I like it. All right, so we're given some information. It says, suppose that the sine of alpha is 12/13, and this is a quadrant 1 angle. Oh, sorry, quadrant 2. That's a quadrant 2 angle. And then it also tells us that the sine of beta is 3/5, and that is a quadrant 1 angle. Okay, so now we want to find the exact value of a variety of things. The first thing is that we want the cosine of alpha. Second thing we're looking for is the cosine of beta. The third thing we're looking for, the third thing we're looking for is the cosine of alpha plus beta. So that's going to hint at one of our new formulas. And the fourth thing we're looking for is the sine of alpha plus beta. All right, so cosine of alpha and cosine of beta are actually things you've already done. Okay, so this is, if we think back to when we started really unit circle trig, right? I would have given you maybe the sine of an angle, and I would have told you the quadrant it's in, or told you some information so you could figure out what quadrant it's in. And then I might have asked you to find the cosine of that angle. So we know that angle alpha is in quadrant 2 because we're told that. Okay, so, and we know that the sine of angle alpha is 12/13. So angle alpha is some kind of angle in quadrant 2, right? And the sine, which means opposite over hypotenuse, is 12/13. All right, so we're asked to find the cosine of alpha, so we need the adjacent side, and if we either remember our Pythagorean triples or we do a little Pythagorean theorem, we'll find that this is 5, okay? But keeping in mind we're in the second quadrant, so really that's like a -5. So the cosine of alpha is -5/13. Right? Likewise, for the cosine of beta, if we know the sine of beta is 3/5 and it's a quadrant 1 angle, so we're here, the sine of beta is 3/5, so opposite, here's beta, opposite over hypotenuse is 3/5. We need to find the adjacent side. Well, this is an easy triple to remember. This is your 3, 4, 5. Right, so, and we're in quadrant 1, so cosine is positive, so cosine of beta is 4/5. Okay, so those two things are things that you should have already been able to do. The cosine of alpha plus beta brings in our new formulas. So the cosine of alpha plus beta, we need to remember, is equivalent to the cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. And now we just substitute all of the values we have, because we have every single one of these values above. So we're going to substitute cosine of alpha, we determined was -5/13. The cosine of beta we determined was 4/5. And now we're going to subtract the sine of alpha, which is given to us as 12/13, and the sine of beta, which was given to us as 3/5. And we have to just do our 6th grade math here, right? We can cancel these 5s if we want, and we get -4/13 minus, multiply the fractions right across, 36/65. We need a common denominator. 13 goes into 65 5 times. So if I make a 65 out of the 13, that means my 4 is going to become a 20. Right? All I did was I multiplied 4 by 5 and 13 by 5 to get a common denominator. So 20/65 or -20/65 minus 36/65 is -56/65. So the cosine of alpha plus beta, if I use my sum and difference formulas, or my sum formula, or the sum of cosine formula, and substitute all of the values that I found above, I get negative 56/65. All right, likewise for the sine of alpha plus beta, I'm going to look up my formula, and the sine of alpha plus beta says it is equivalent to sine of alpha cosine beta plus cosine alpha sine beta. So now I'm going to go ahead and substitute all of the values that I have. The sine of alpha is 12/13. The cosine of beta we determined was 4/5. Plus cosine of alpha we determined was negative 5/13. And the sine of beta was given as 3/5. And now again, we do our 6th grade math, 48/65, plus this is going to be a negative. These 5s are going to cancel. This is going to be negative or minus 3/13. Common denominator is again 65. 13 times 5 is 65. 3 times 5 is 15. So 48/65 minus 15/65 is 33/65. All right, so these are kind of fun. So it applies a whole bunch of things that we've already learned, right? You're given some information about an angle, 2 angles really. You're told where it is, which is going to give you some indication of the sine of the cosine, or any other of the other trig ratios that we're trying to find, right? The SIGN sign, right? So the cosine of alpha must be negative because we're in quadrant 2. Cosine of beta was positive because we're in quadrant 1. We determined those values, and then in order to solve part 3 and part 4, we just applied our new sum and difference formulas and substituted our ratios. Okay, and finally we have an example of how we can verify an identity using these new sum and difference formulas. I'll be honest, it's not super earth-shattering. Okay, it's really just applying the formula and then doing what we have been doing with identities to verify. All right, so we want to verify the following identity. You notice here that we've got the cosine of a difference, so we're going to apply the cosine of a difference formula right up here. So instead of writing the numerator of this side as cosine of alpha minus beta, we're going to rewrite it using our formula. We're going to rewrite it as the cosine of alpha cosine of beta plus sine of alpha sine of beta, and we're going to write that all over sine of alpha cosine of beta. All right, so if we look at this, we've got some alphas and we've got some betas. There's no common factors. There's really nothing we can do with this side anymore. Okay, so now the question is, can we make the right side of this identity, this cotangent alpha plus tangent of beta, look like this? Okay, so let's see. Cotangent of alpha. I don't really like cotangent and tangent, so I'm going to rewrite them in terms of sines and cosines. Right, so cotangent of alpha I can rewrite as cosine of alpha over sine of alpha. And tangent of beta I can write as the sine of beta over cosine beta. Now be careful, because these are a little bit different than the ones we've been doing because we've got 2 different angles. All right, so when I get my common denominator is sine alpha cosine beta. When I multiply this side by cosine beta, it's not cosine squared anymore, right? Because alpha and beta are 2 different angles. Okay, so I'm going to multiply over here by cosine beta over cosine beta. And I'm going to multiply here by sine alpha over sine alpha to get my common denominators. Right, but again, cosine beta times cosine alpha is simply cosine alpha cosine beta. It's nothing else. It's nothing other than that. And that's going to be over cosine beta sine alpha plus sine beta sine alpha over cosine beta sine alpha. And take a look. This, once I combine these numerators, cosine alpha cosine beta plus sine beta sine alpha all over cosine beta, sine alpha. Things are in a little bit of a different order, but this and this are exactly the same. So I verified my identity.